So, what's going here is when white light is used in YDSC, Ydse experiment, interference patterns due to different colors of white light overlap incoherently. The central bright fringes for different colors are in the same position and therefore central fringe is white. For a point P, except for any arbitrary point, so for P for which if you consider the path difference is lambda by 2, where you can take any wavelength. Say for example blue wavelength 4000 angstrom units, which represents the wavelength for the blue color. The blue component will be absent and the fringe will appear red in color. Slightly further away, where S2Q minus S2Q equal to lambda red by 2, where lambda r you can take it as wavelength of red, which is approximately 8000 angstroms, is the wavelength of red color. The fringe will be predominantly blue. Thus, the fringes closest on either side of the central white fringes are red, and the farthest will be blue. After few fringes, no clear fringe pattern will be seen because they will overlap. Okay, so what you can understand from this is when you use white light, if you use any monochromatic light, so one source is there, any particular color, red color or blue color, any monochromatic light or green color, whatever it is, like a laser light, any particular color laser light, and the light, from that light, if you allow that light to pass through slits, they will act like two sources, different sources, and hence we will get two waves of same frequency, same amplitude or different, but of same frequency. Then they will be considered as coherent sources. They will interfere. Whereas if we are using white light as the source, and hence if the white light is allowed to pass through the two slits, same white light. In this white light, what you can understand here is when white light is used in the Young's double slit experiment, the interference patterns due to different component colors of white light overlap. When white light comes here, different colors will be there, they will overlap. Different colors will overlap. So visual, some colors will be there, right? Overlapping is characterizing fringe or slits. Not just while forming the screen. So when they overlap on the screen, usually they're not forming it systematically, so we can call it incoherently. The word we use. So when they mix up or overlap, the central bright fringe for different colors are at the same position. Actually, for all these different colors, central bright fringe will be for the central bright fringe will be at same point. That means, say for example, if you are using only red color in both slits, they will form bright fringe at the center. If you are using blue color, for that central bright fringe will be formed at the center. So any color in which you are violet to red, any color if you use indigo blue or red, blue predominantly at the lower and red on the other side. Any color if you use, bright one will be at the middle point. So in this every color, due to every color, if you consider the path reference at the center will be 0, and hence they will form bright fringe of that particular color. So now all the colors, bright fringes of all colors will mix up at the center. So this mixing will give you white color. It will give you white color. So what you can say is general bright fringes for different colors are at the same position. Therefore, the central fringe is white. Let us just pass this to another online students also. So, okay. So, what you understand is, if you have a single color, for that, let us discuss here with the help of the what they call diagram only. If you have double slit experiment, if you passes a particular color, a single color, this is slit 1, this is slit 2, by drawing that light from the particular source, monochromatic light if you are using, these two will interfere at the center with zero path difference, so you get bright fringe. What is central bright fringe? Whether this color is any of this UGR, whether it is violet, indigo, blue, green, yellow, orange, or red, any of these colors. If you passes violet, you get central bright here. If you passes indigo, you will get central bright here. If you passes blue, so you will get central bright here. If you passes green, yellow, or orange, or red, any color, central bright will be here only. So if you passes white light, usually it is a combination of seven colors. All colors what is that? The distance traveled by the path length traveled by every color will be same. Every color will be same, and hence they will mix. Bright fringe due to all colors will form here. So they will give you what you call as central bright combined central bright fringe as white fringe. Central combined central bright fringe as white fringe. The next point is central fringes for different colors are in the same positions, therefore central fringe is white. Next point is for a point P. So for any point, let us say again for the same, this is a S1, S2, this is central point, this is our screen. Somewhere here for a point P. You can say somewhere over here a point P. For a point P, for which this is S2P and this is S1P, so that the path difference, if you consider it particularly any color, till now we have specifically not discussed about blue color, red color. Some color light we are used to use the word light. Here, if you consider blue color, then path difference is given by this S2P minus S1P delta X. So here this delta X, which is nothing but S2P minus S1P, is equal to what you can say here is, if path difference is lambda by 2, and if the color is blue, then wavelength of blue by 2, if you are considering, okay, where if lambda b is a blue color with particular wavelength approximately 4,000 angstrom unit, which represents the wavelengths for the blue color. What is that? This represents the wavelengths for, okay, the blue color component will offset here. When the path reference is lambda by 2, this belongs to destructive interference. Destructive interference. So destructive interference of light. Usually we say light, but if you say a particular color, the wavelength of the color, what is that? The light belongs to this wavelength will disappear in the destructive interference. So you can actually take this as a 2n minus 1 into lambda by 2. It's not just lambda by 2. 2n minus 1 into lambda by 2. First one, if you consider 1, n equal to 1 means we get 1 lambda by 2. That is the meaning of it. That means that first fringe due to this is a dark fringe means there is no light. The blue has to be there, but it is not there means it is disappearing. That is the meaning of it. So you can say that the blue component will be absent and fringe will appear in red. That means it shifts to some other place. This is called a redistribution. That is what in the first session we have discussed about what you call interference. Interference is nothing but the phenomenon of redistribution of energy on what is that superposition of the to two waves. Superposition of two waves of same color means from one place to another place it will redistribute. If different colors are there means from one color to another color it will redistribute. Correct? That is the meaning of it. So the fringe will absent from here, then it will be shifted. And shifted and hence it will appear in a red color, I can say. Right? Same way, if you are using a red color, provided if the path difference for the red color at the point P is equal to what do you call integral multiple of lambda by 2. That is, say for example, the first fringe is at lambda by 2. Then we can say that here, what is that? If wavelength lambda, if it is belongs to like if S2P minus S1P is equal to lambda of red by 2, where lambda r is nothing but wavelength for red, then the fringes will predominantly blue because the red will be absent there. It will shift to blue. So you can say we get blue. That is the meaning of it. Thus, the fringe closest on either side of the central white fringe will be first. Instead of blue, will get red, and instead of and the farthest will appear as blue, red and blue. It will appear like red to blue. So predominantly, but actually speaking, here instead of blue, you should have indigo violet. But predominant one will be blue. It is more visible. That's why we consider blue instead of violet and red. Otherwise, you can say if violet is given, violet will be in place of blue, violet should be there. Like that, you have to consider. Okay. So first, if you consider here, what you can consider just near the central bright fringe. This is the central bright fringe. Near the central bright fringe, what is given here? The fringe is closest on either side of central fringe. This side or this side, closest to either side of the central bright fringe will be red, and farthest will be blue. Somewhere here will be blue. Blue means you can say violet also. Here is violet also. Instead of blue, you can also call this as violet. So nearer to central bright fringe will be red. Farthest to central bright fringe will be blue or violet. Blue or violet. This is what you can understand from that. Okay. Okay. This option missing fringes is okay, right? Missing elements is okay, right? Plus anything else? Let me. Hmm. How to recall? For that, just I told you that try to prepare a simple synopsis. So now, let us say wave optics is completed. Now so because entire wave optics we have written the weekend exam this week. What you have to do is today itself, because the next week portion we have not started. Sit 1 hour, maximum 1 hour. After even go to dark and sit and prepare synopsis synopsis of wave optics. Wave optics. How to recall all the concepts without forgetting very easily. So first in the wave optics topic, try to write the just this you have to write like even the synopsis also you have to work like trial and error way in your own way. So you can try to first prepare the main contents first ones. So main contents means entire wave optics consists of only three concepts. One is interference, interference, and the second one is diffraction, diffraction, and third one is polarization. Okay, so the moment you come across the name wave optics means these three should flash in your mind. That is first point. Now, while preparing the synopsis, what you have to do is you can say you prepare this you just mention these 3 points once. Then go to the next page. You take one next like you can otherwise just one first you mention this, then the next down you write like this first. Under this you take down interference. Interference. In under interference, what we have discussed. Some basic terminology of this and that you can try to recollect back. And the first thing is what do you call it? Principle of superposition and interference of waves. Interference of general waves. Right? Then we have come to YDS. Before that, we have discussed about interference of any two waves. Right? General mechanical waves also. Interference. Simply, we have discussed about interference. Here we have used the principle of superposition. We have used the principle of superposition. Then, under this, what we have studied? If two waves, only two waves, y1 and y2 are there, combination of this gives you a new wave. We can say resultant wave. It is equal to vector sum of the displacement of two waves. It is called principle of superposition. This also been vector form. Mathematically, here you can just simply you can write for your remembering purpose where y1 is you can say same amplitude or different amplitudes. Let us say different amplitude a1 sine omega t plus. You can write here in terms of phi or kx, phi or kx form. Okay, is it clear? Phi, let us say phi 1 and y2 is equal to a2 sine omega t plus phi 2, two waves. On adding this, you have to just immediately try to get some few steps of this which we have discussed and try to give the expression for resultant displacement. It is equal to resultant amplitude into sine omega t plus phi. This phi is nothing but phase difference. You can say delta phi also. The phi is phase difference which is equal to phi 2 minus phi 1 of the individual waves. And AR is what? This is resultant wave where AR is nothing but resultant amplitude which is given by actually you have to remember the intermediate steps that while deriving A cos phi what is it? A1 plus A2 cos phi is A cos phi and the other one is A sin phi we have taken, right? These intermediate steps, if you remember, then you can understand and you can remember this as a whole. Here AR is equal to AR square is equal to A1 square plus A2 square plus 2A1 A2 cos phi. AR square equal to AR is equal to square root of this. Write this formula corresponding to this intensity of resultant wave. Write down this formula. Yes. What is that? I can write to write this intensity better to square on both sides. Write down this as AR square. AR square gives you IR. AR square gives you IR because intensity is directly proportional to AR. Then AR is equal to I1 plus I2 plus 2 into square root of I1, I2, the only root is only for this into cos phi. Right? Some special cases also try to write here. So likewise, if you write the only formula, not the detailed discussion. So special case when I1 equal to I2 equal to I naught, then IR is equal to 4 I naught into cos square 5 by 2. Here you should remember the again relation between phase difference and path difference. So yes, that also. Then remember delta phi is equal to 2 pi by lambda into delta x. Then by using this, you write down this IR is equal to 4 I naught into cos square. In place of delta phi, you put delta phi, then you will get 2 cancel, then you will get pi by lambda into delta x, or simply you can put x also. So these are one set of formula you get under this. Then YDSE. Then put YDSE. Under YDSE, you can mention 3 points. 3 points. First point for constructive interference. Even here also under interference itself, but generally you can put the constructive interference condition, destructive interference condition in terms of phase difference, in terms of path difference. Generally, before this itself, you have put constructive conditions for constructive interference, then destructive interference, etc. For the delta phi is equal to what is that, integral multiple of 2 pi, right? For destructive interference, delta phi is equal to 2n minus 1 into pi by 2. Similarly, path difference delta x is equal to, from this, is equal to lambda by 2 pi, right? 2 pi 2 pi gets cancelled, you get n into lambda. This is for this, it is equal to 2n minus 1 into lambda by 2. Here when you say 2n minus 1, 2n minus 1, then n will take values from 1, 2, 3 and so on. Okay, if you take 2n plus 1 also you can take. 2n plus 1 if you take, n will be taken from starting from 0. 0, 1, 2, 3 and so on. That also you have to remember. Then YDSC. In YDSC, for central, for bright fringes. What is the position of and the bright fringe? Position of and the dark fringe. This point, by using this you have to do then YDSC. Then you have to write YDSC. Hmm? Then you have to write YDSC. The experimental setup diagram also you have to draw and remember like this briefly. Okay, S1, S2, D will be this. Then screen at a distance D. This is central bright fringe. Then again write down for another diagram for another point. This is the one. This is one. Then at any arbitrary point P. So then you have to write position of nth bright fringe is what? Position of nth dark fringe is what? Fringe width is what? Write down this formula. Right? Like so. What do you see? Then some special cases you can write here. When it is the entire setup is immersed in liquid of refractive index, what happens to these positions? Everything is reduced by you, whether it is a position of in dark or bright or even beta, right? Special cases, special cases. So here in a medium, in a medium, what happens to all this? Then second one, you can take missing wavelengths or interference of white light, for white light, for white light, then missing missing wavelengths, right? So and another next fourth very important one is introduction of slab. Introduction of slab. What happens to the path difference, optical path difference, that you have to introduce. So this point immediately, this one point should come. Got it? Then that's it. With that, it will be finished. Then still films and all not required anyway. Then we have to take diffraction. Diffraction is simple. Only one. What is that? First, what is diffraction? Some types also just try to mention diffraction. Then put like this briefly types. What is that? Fresnel and Fraunhofer. Fresnel and Fraunhofer. Then you can mention uh, just how to represent this, the conditions. For Fresnel, both screen and slits will be at finite distance. For this, they should be at infinite distance. So that condition you just you mention like this with the diagram otherwise. Okay. Then usually we use Fresnel. Fraunhofer means also should you should mention that length should be there. Then in this single slit experiment, write down next in single slit diffraction. And at this write only 3 points. First point is what is that? For diffraction minima condition. Then second one, diffraction secondary maxima. Here this is little important. Secondary maxima, right? Then primary maxima. So write down the positions positions of minima means path difference conditions first, path difference, then positions, then try to write the angular width. This gives with the help of this is a normal linear position. Similarly, angular position, theta. So we have those expressions, right? Angular position for nth bright or nth dark positions. Write down this expression. That's it. With this, then polarization. Likewise, write the list. Then automatically you will remember all the points. Just simply, if you will go after 1 month or 3 months, also if you just open that and if you go to this for 10 minutes, you can recollect that. But regularly, you have to, whenever you get time, if you go to that, you can remember. Okay, so prepare this synopsis today itself. And try this.